So today we are going to talk about if we enter a catalyst in our chemical reaction, what happened? In this case, some people will call it as a catalytic chemical reaction or catalysis. So catalysis is an increase in the rate of chemical reactions by adding a catalyst, which is not consumed in the catalytic reaction, and it can continue to act repeatedly. So it is not consumed and also can act repeatedly. And the purpose here is to decrease the activation energy. So now the reactant A and B can easily to overcome this and lower energy barrier to generate C and D. So this is the purpose for ending the catalyst. So in order to remark that or remind yourself that catalyst is not going to be consumed and can act repeatedly. So usually we will use the RZ to represent the catalyst be ended in these chemical reactions. Also, and at this situation, the driving force between the reactants and products haven't been changed. Just the only thing you changed by ending the catalyst is the energy barrier in these chemical reactions. And as we mentioned, what's the factors which can modulate the rate equation? The rate equation expressed like the rate constant and concentration dependence, right? So based on this rate equation, you know if the chemical reaction we talk about is a homogeneous chemical reaction, you need to, as long as you pick the chemical reaction, then you already have the activation energy is a constant, right? And the only thing can change will be the temperature, and also if the reactants belongs to gas, that will be the partial pressure. If the reactants belongs to solid or phase or the liquid phase, that will be expressed like a concentration dependence, right? But if the reactions belongs to heterogeneous chemical reaction. That means the reactants, these reactions involve two or more phases, right? React together. So in this kind of situation, you also additionally you need to consider the heat and mass transport among different phases. So I'm going to give you an example here. Is the burning of the coal. So what's the reaction of the for the burning of a coal? Usually people will say, oh, oxygen react with the coal, then we will generate probably carbon dioxide, something like that. Yes. But in this kind of case, when I ask you about the reaction rate equation, you need to additional consider the transport of this oxygen. So the oxygen need to diffuse or be transported to arrive the surface of the coal, then they can start the reaction, the burning chemical reaction. So actually it's considered as a series reaction. The first one is transport of the oxygen, then the second one will be the burning chemical reaction. Okay, so this is additional we need to concern when we have a heterogeneous chemical reaction. So now I have a question for you. We have a solid A react with solid B, then we will generate solid C, and we have a gas. If this chemical reaction occur in a sealed container or it in an open space, any difference in generation rate of the product C? Which one is faster? Probably the answer is open space, because based on the Le Chatelier's rule principle, you know, if this chemical reaction happen in a sealed container, then the gas, the product D cannot goes out, right? So that will allow the concentration of product D will increase. So based on the Le Chatter's principle, this equilibrium of this chemical reaction will have chance to be reversed to a left-handed side. But however, if these chemical reactions happen in the open space, so that will allow the gas D go out always, so that will lead the reaction always toward to right-handed side. Okay, and but the other thing is, based on this rate equation, if you measure the consumption rate of reactant A at different temperature, then the slope based on the after fitting, you will get the activation energy because the slope is minus EACT over K. Okay, so next I'm going to give you some examples. Not examples, different units for the rate equation. Okay, so the Ri sub I equals to, this is the dNi over dt is the numbers of either is consumption rate of reactants or the per generation rate of products and per reaction volume. And this Ri prime is the consumption rate of reactants or generation rate of products, but is per reactant mass. And this Ri double prime actually means that this is the consumption rate or generation rate, consumption of reactants or generation rate of products, but is per interfacial reaction area. Some people probably were curious what happens when we use this as a unit per interfacial reaction area. Usually will happen in heterogeneous chemical reaction when the reaction area region is on the surface. For example, like the burning the coal, the reaction only happens on the surface of this coal, right? So the unit will be more suitable to use as a per interfacial reaction area. Oh, okay, so the rate equation can express like rate constant and also concentration of reactants and also reaction orders. So the rate equation will depends on the rate constant, concentration of reactants, and also the stoichiometry coefficient of the reactants. Okay, this we call it as a reaction order. Okay, so next I'm going to give you some picture about the scale of the reaction rates from 10 to minus 4 toward to 10 to 4, and the unit here will be the mole of A disappearing per cubic meter per unit time. So this is the slowest one, this is a faster one. So slowest one, we give you example is sewage treatment. Is the rate equation, the order will be like a 10 to minus 4. And if the human at rest will be range between the 10 to minus 2 to 10 to minus 3. And the jet engine will be range to 10 to 3. And the rocket engine will be to 10 to 4. Okay, so let's give you an example to calculate sorry, to calculate the rate equation for this chemical equation. So now it's a human being with 75 kilograms. He can consume 6,000 kJ food per day. So how to generate the energy by taking the food? Then obey this chemical equation is a glucose react with the oxygen. Then you will get the carbon dioxide and water. Then you will get the extra energy is around 2,816 kJ. So these people take a 6,000 kcal of food per day. So how much glucose, or what's the consumption rate of the oxygen? We hope you can calculate based on the information provided on these questions. So the consumption rate of oxygen, the unit here will be the consumption rate of the oxygen per univalent. So what's the consumption rate here? Is, as we know, he takes 6,000 kcal food per day, and based on this equation, we need to know how much glucose he take, right? This is a glucose. So we use a 6,000 to divide it by 2,816 kcal. We know how much moles of glucose he take, and times the 6, so we got the total oxygen be consumed. And also this is we know, and the unit will be in moles. And the volume of the human being will be used the weight divided by the theoretical density of the human being. So finally, we'll get the results for the consumption rate of oxygen will be ranging to the 10 to minus 3 order, will be the same as we get here is 10 to minus 3. Okay, so next, this slide is going to show you what's the elementary and non-elementary reactions. So elementary reactions means that the chemical species react directly to form the products in a single reaction step and with a single transition state. That means the A directly react with B and generate R. So when you write down how to write the rate equation? So the consumption rate of reactant A will be equals to consumption rate of reactant B, because I react one A react with 1B, then generate 1R, so R. And here minus means the consumption, and generate, we use the positive sign. So we consume 1A and 1B to generate 1R. So we got a minus here and the positive for the products. And this is elementary reaction, means like the rate constant times the Ca to 1, because the coefficient here is 1. Cb to 1, also coefficient here is 1. So we got the rate equation here. And also, we give you the other example. For this one is 1A react with 1B, you generate 1R, right? But now if we are not, the coefficient is not exactly the same. So how to modify the rate equation? So for this case, if this equation belongs to elementary reactions, tell you 1B directly react simultaneously with 2D. 1B bond with 2D in the meantime, then generate 3T. So when you try to write down the consumption rate of B, then you can write down the KB and CB to 1, CD to 2. If you try to use this consumption rate of D, then you will write down the KD, CB to 1, CD to 2. And you want to know the generation rate of T, also the KT, CB, CD squared. So now you know, first thing is we consume 1B, react with 2D, generate 3T. So RB, RD, and RT definitely are not the same, right? There's a relationship between RB, RD, and RT, because you use 1B to react with 2D and generate 3T. So there's a relationship between the consumption rate of B, D, and T. And compare these three, the concentration dependence are the same. So I believe, based on these results, we know KB, KD, and KT have the same relationship with the consumption rate, or the rate equation. R. Okay. So this is the elementary reaction. So as long as you confirm your chemical reaction belongs to elementary reaction, that will be easy to you to formulate the rate equation, because the reaction order is the same with the coefficient shown in the chemical equation. But if your chemical reaction is non-elementary reaction, it's nitrogen. For example, nitrogen react with hydrogen and generate ammonia. And when I find that the rate equation expressed like this complicated way, then I can, as long as I find this way, I find its rate equation, then I can confirm the chemical equation we discussed above is definitely not a elementary reaction. It's definitely, because this complicated rate equation definitely is assembled by what? It's assembled by several or multiple elementary reactions. So as we mentioned, a non-elementary reaction definitely is composed of multiple elementary reactions. So that will allow its reaction rate like a less complicated format. And in order to formulate or confirm the rate equation, you need to find out what elementary reactions assemble this or reconstruct this non-elementary reaction. You need to find them out. Then you can explain why the rate equation looks like this. Okay? So based on the rate equation, we can know whether the chemical reaction you're dealing with is elementary reaction or non-elementary reactions. Okay, so following, I will give you two examples is the non-elementary reactions. To reconstruct the kinetics model of non-elementary reactions. The first one is the A react with B, and we will generate a product AB. And from your experimental observation, then you got the generation rate of product AB is equals to KCB squared. So based on this experimental observation, we know this reaction definitely belongs to non-elementary reactions. Otherwise, it will be, the rate equation will be like this, right? KCACB, but it's not. So this equation definitely is a non-elementary reaction. So to dealing with these non-elementary reactions, what we are going to do next is to reconstruct the kinetic model for these non-elementary reactions. That means we need to find out what elementary reactions construct these non-elementary reactions. So first of all, we need to make an assumption. We assume it is a two-step reactions, and both these are elementary reactions. And elementary reactions construct these non-elementary reactions. So it would be probably like A is not directly react with B. Instead of that, it's like a 2B. B react with B to form a intermediate B2 star. And the forward rate constant K1, backward is K2. And as long as we have an intermediate substance B2 star, then this B2 star react with A, then generate B and AB. And the forward reaction here is K3, backward is K4. So if you can check, you sum these two elementary reactions, you got A plus B equals to AB. It's the same as what we are talking about, right? So in order to check whether this model is correct or not, to reconstruct this non-elementary reactions, so I will show you how to check this. So based on this, the second one, we can formulate the generation rate of product AB will be equals to, generate this one, K3 B2 star times A. This one direction, and K4 is minus, because if the direction go to the left-handed side, will decrease the concentration of AB. So it's K4 B times AB. Okay, so we got this one. The final goal here is we are going to get the results for RAB and compare with this one to see if the results for RAB is proportional to CB squared. If yes, then both these models are correct. This model is correct. Okay, so here we don't have idea will be the concentration of B2 star, right? So how to get a B2 star? So we need to make a assumption here. B2 star is an intermediate, molecular intermediate. So we assume it is a steady state approximation. So the intermediate B2 star, the concentration is very small, and also this concentration does not change with time. So next, I can formulate the generation rate of B2 star. So B2 star, K1 is going to increase and K2 is going to decrease, right? So let's try to formulate the the RB2 star. So first of all, I want to use this one, right? Is if I use the consumption rate of RB would be K1 B2 B concentration of B squared, right? But this is minus RB, right? But don't forget, if you consume 2B, you will get only 1 B2 star. So if I express like a minus RB, then you want just 1/2 of minus RB, right? So here, don't forget, the relationship between RB and RB2 star is you spend 2B, only get 1 B2 star. So here, if you express like a minus RB, we will get a 1/2, okay? And next will be, so I use this RB will be K1B star, or B2 B squared, and RB2 star will be just 1/2 of RB. Okay, so this is we finish the K1 part, and K2 will be what? K2 will be decreased, so it's minus K2 B2 star, and K3 is going to decrease, so also minus B2 star and A, and K4 is going to increase, so it's a positive K4 and AB, and this because does not change with time, so this one approach to 0. So based on this assumption, you can get the B2 star and substitute these results here. And after calculation, we got this complicated results. But if we take a look at here carefully, in order to allow the generation rate of AB proportion to B squared, then the only way to get these results is we assume the K2 is very small. So what's the K2 very small means? The K2 small means that B2 star have only small chance to separate, then becomes to 2B. Okay, so if I make this assumption, then you can drop this term out in K3 and A, so the results will perfectly proportion to B squared. So based on these results, we know we successfully construct the kinetic model for this non-elementary reaction, and also we know that's the intermediate B2 star, and B2 star is only have a small chance to separate into 2B, okay, because K2 is small. Yes. So you also can use some material analysis technique to measure what's the B2 star. Yes, you have chance to do that. Okay, so this is how we reconstruct the kinetics model for these non-elementary reactions. By what? By starting from the experimental observation. So the other case also is a catalyzed non-elementary reaction. We added the enzyme into this reaction. So the A will generate R. And we also have 3 experimental observations here. And the first one is the consumption rate of reactant A is proportional to the concentration of initial enzyme. And the consumption rate, the second one is consumption rate of reactant A is proportional to concentration of reactant A only at low concentration of A. And when you increase the concentration of A to high concentration, then the consumption rate of reactant A is independent with concentration of A, reactant A. So we have these 3 experimental observations. In order to reconstruct the kinetics model, we also make an assumption here. The A react with enzyme and generate intermediates X, and the forward rate constant is K1 and backward K2, and this X will have chance to generate R, product R, and also E. You need to put the E, as you know, the enzyme is not going to be consumed and can be used repeatedly, and with a rate constant 3. So following deviation, just want to confirm whether this assumption is correct or not. Would be whether this result will be also fit with what we observe in our experiments. Okay, so based on the second one, we can have a generation rate of product R can be expressed like the dr over dt, K3 concentration of intermediate. So now we don't know this one, right? As long as we know the X concentration of intermediate, then we can get these results. So following part is going to make some assumption. Here we assume the initial concentration of enzyme equals to residual enzyme plus the X. And also the concentration of intermediate does not change with time. Under this assumption, then we also can write down the generation rate or consumption rate of dx over dt. One is going to increase the concentration of X, so it's K1 AE K2 X minus K3 X, and this equals to 0, so we got the, and also here E can be substituted as E0 minus X, so we can get the X expressed like this, and we take this into here, so we will get the generation rate of product R can be expressed like this, and we copy these results to next slide. And if you take a look here, we have a K1, K2, and K3, right? Because of K1, K2, and K3. So we divided by K1 together. So if we divided K1, so the top portion we have is K3. And this will be K2 plus K3 divided by K1. We call it as a Michaelis constant, so we use M, and divided by K1, so we got here. So this is the result we have. So now what you have here, the generation rate of product is equals to this. So let's try to check the experimental observation, whether the results is fit with what we observe in our experiments. So in the first one is we say the generation rate or assumption rate, consumption rate is proportional to initial concentration of enzyme. Yes. It fits with the first observation. And the second and third observation, only the second one is when we have a lower concentration of reactant A. This is lower, it's small. This is large, right? This small, you can drop this term out, and this is quite large, right? At this situation, we find that the generation rate or consumption rate of reactants or generation rate of product is proportional to concentration of reactant A. Yes, is fit with what we observed. By the way, we also yes, this is small, this is large. M large, what means M large? M large means what? K2 and K3 is large. What's the K2 plus K3 is large means what? As long as you generate X, then immediately be consumed, either converted to left-handed side or converted to right-handed side. So you don't have enough. So lifetime of X is short. So in this case, you have X has a short lifetime because A will convert it into R immediately. So that's why a reaction rate is proportional to A. And the other case, the third one is what? Is as long as you increase the concentration of reactant A to high A, then this is small, right? This is large, you can drop this term out, and you only have this term and you drop this term out. So you find the generation rate is nothing related to concentration of reactants. So independent of concentration of reactant A. But in this case, what is this very, very small? Means the K1 is large. So what's the K1 is large? K1 is large and this is very small means that we converted, we have bunch of X, but a few of them be converted to R or backward. So we have X has a longer lifetime. Okay. So this is the first of all, we successfully reconstruct the kinetic model for this non-elementary catalyzed reactions, and also we know we have chance to monitor the intermediate substance, right? And how to measure that when you try to increase the concentration of A, then you have chance to know what is X. By using the material analyze tool, you have chance to know what's X, because at this situation, X has a longer lifetime. So you have chance to monitor what is X intermediate in these reactions. Okay, so next I'm going to move to, we finish how to reconstruct the kinetics model for non-elementary reactions. So next we are going to move to the temperature dependence of the rate constant. Based on the rate equation, you know the first term is the rate constant and embedded it with the temperature dependence in the rate constant. And the second term is the concentration dependence part. So K equals to K0 exponential activation and minus activation energy divided by RT. Okay, so when you want to formulate or try to know the temperature dependence, usually we will perform at the same concentration. So we will keep the Ca, Cb at constant. Then we just change the temperature to T1 and T2. So you will get the R1 expressed like this and R2 expressed like this. Okay? So some people probably, because it will focus on the temperature dependence of rate constant, so you can plot the log K over 1 over T. So the slope will be minus E over R. Based on the slope, if you have the slope and this slope, this one has a higher slope, that means the activation energy is higher than this one. So it will say the K with higher activation energy is more temperature sensitive. What's the more temperature sensitive means? This is high-low. During the same temperature regime, between the 463K to 1000, during the same temperature regime, and the K, the changes of K for high temperature regime is higher than this with the low temperature regime. That means that's the meaning for why K with higher energy is more temperature sensitive, because when you change the temperature, then the K decrease or increase a lot than that one with lower energy one. And the second reminder or point will be the K at low temperature region here is more temperature sensitive than that at high temperature region. What this means? At a low temperature region, when you try to twice the rate constant, you only just increase the temperature by 100 K. But at higher temperature region, for example, like at 1000 K, and you want to twice the temperature, rate constant to twice 100 to 200, and you need to increase the temperature to 1000 K. So this means that low temperature region is more temperature sensitive than high temperature region, where you try to twice your rate constant. And the third one is this log K versus 1/T can help you to determine the reaction mechanism, because by fitting you know the activation energy, right? And also I mentioned, if after fitting you got the strain line, that means only one activation energy. So that means only one chemical reaction involved in doing this temperature region. But however, if you got, after fitting you got this curve, it's not a straight line or this curve. What does it tell you about your reactions? For this curve, you can simply fit it with two reactions, chemical reactions corresponding to reaction 1 and 2, and based on the slope you can find the E1, higher E1. This slope is higher than this one, so I believe activation energy E1 here is larger than this one, right? So this tells you that during this temperature region, at high, there are two chemical reactions involved, but at high temperature region, is reaction 1 dominate, and at low temperature region is reaction 2 dominate. Okay. But the data show you that actually the data is the sum of these two reactions. So this data point actually is the sum of this, for example, like at this high temperature, then you got the K here, right? And this is the sum of this value plus this value. So you got the experimental data. And for low temperature region, we can say is a reaction 2 dominate. But this K actually is also the sum of this one, reaction 1 and reaction 2. But reaction 2 dominate at this temperature. So here, based on this curve, we know there's two reactions involved in this during this temperature region. But at high temperature is R1, reaction 1 dominate. For at low temperature is reaction 2 dominate. And let's check, are there any clue to tell you based on which dominate, is a fast one dominate or slow one dominate? For this case, at this high temperature, we find that it's faster one dominate, because this one is faster. Larger K means larger R, so faster one dominate. And at the low temperature, K2 is here and K1 is here, so also the fast one dominate. So no matter is at high temperature or low temperature, always the fast one dominate. So we have two reaction, right? Always fast one dominate. So I can expect the relationship between reaction 1 and 2 is a parallel reaction. Because for parallel reaction, always the fast path dominate whole reactions. The same idea you can perform for this curve. If you have to measure the log K at different temperature, then you find, I have this curve. And this curve imply that after fitting, you got two reactions involved during this temperature regime. But at high temperature, I believe it's reaction 2 dominate, and at low temperature, it's reaction 1 dominate. And also at here, you can find that always is the reaction 1 here at this temperature region. The K is quite large, right? And compared to this one, so it's low 1 dominate reaction. And for this one, the reaction 2 has a higher K compared to this one, but this is a lower K for reaction 1, right? So for this reaction, interesting, always is a slow 1 dominate. So you have two chemical reactions and always slow path dominate. So usually the relationship between the chemical 1 and chemical 2, reaction 2, is the serious reaction. So that will always allow the slow 1 dominate whole reactions. Okay? So I'm going to give you a summary here. So the rate equation consists of the concentration dependence and also the temperature dependence. And for heterogeneous chemical reaction, you need to take care of think more about the transport part between the different phases involved in these heterogeneous chemical reactions. And regarding to non-elementary reactions, first of all, as long as you know the rate equation, then you can determine whether your interesting reactions belongs to non-elementary reaction. If yes, it is non-elementary reaction, please, you need to reconstruct the kinetics model for this non-elementary reaction. You need to find out what the elementary reactions assemble or construct these non-elementary reactions. You need to find them out. Okay, so this is how we say like you need to reconstruct the kinetics model for the non-elementary reaction. And regarding to less important analyze method is a log K versus 1 over T or log R versus 1 over T. As long as you know the we can measure the R, right? So as long as you fix the concentration of the reactant A and B, then log RA over or log R1 over R2 will be equals to log K1 over K2. So this is, some people will use the log R versus 1 over T. Then you also can determine based on the fitting, you know the activation energy and also the rate limited step for whole reactions. Okay, so if if you got a one straight line, then you know only one chemical reaction involved, then you can get the activation energy, right? And if it is a curve, then you can know you need to fit after fitting, then you can get the corresponding activation energy for these two chemical reactions, and also know at specific temperature region which one is dominate whole reaction rate. Okay, so today we just ended here.